Welcome to another physics class. Today we are going to look at another topic, which is work. And as I promised, under this platform, that we are going to take each topic from the fundamental level or grassroots. So today, as topic, work. Work can be simply defined as the product of force and the displacement in the direction of the force. Again, work can be simply defined as the product of force and the displacement in the direction of the force. That is, in physics, before work can be done, there must be a force acting on a particular object in a particular direction. The displacement must be in the direction of the force. Now, according to the definition, this is a load placed on this table. For work to be done, force must apply. And if this thing move from here to here now, then the displacement must be in the direction of the force. This is where the force will be applied. Moving like this, as it's moving, it means work is being done. Moving in the direction of the force. That is, as it's moved from here to here, that's displacement. The force applied in the direction of in this direction, so it means work has been done. That is, if it's moved, as I said, from here, as it's moving, work is being done. Work is being done in the sense that the force is in this direction and the displacement is in the same direction. Therefore, we can now say work is done. That is why we divide work as the product of force, the force applied to this thing, and the displacement covered in the direction of the force. From here to here now, with the displacement covered, and it takes place in the direction of the force. Then work has been done on this small box. Now to write work in the product of force and displacement covered in the direction of the force. The product of force and the displacement covered in the direction of the force. That is, for work to be done, there are two quantities to be considered. One, force that apply to that object, and the displacement covered in the direction of the force. That is, as I said the other time, when force is being applied to this box, force is moving this box now, and they cover a certain displacement. And the displacement, you can now see, is in the direction, the same direction of the force. Then we have work, what we call work in physics. Mathematically, work is equal to force multiplied by displacement. That is, W for symbol of work is equal to F multiplied by D, where force, F is for force and D is for displacement. Now, from this one now, can now say that the unit of for of work are 1. According to this formula, force is Newton and displacement is meter. So that's Newton meter. And again, 2. Force can be measured in kilogram per meter square. That is, it can be for force, that will be kilogram say force is equal to ma, that kilogram meter per second square. And mind you, this is another meter that is multiplied by meter again. Then it will now give us kilogram meter square per second square. That is kilogram meter square per second square. That is the second unit of work. And this second unit, that is kilogram meter square per second square, is what we call the basic unit. Basic unit of work. Basic unit of work. Why is it basic unit? Because all the units here are from fundamental quantity. Kilogram is for mass. Mass is fundamental quantity. Meter is for length. Length is fundamental quantity. And second is for time. Time is fundamental quantity. So since all those quantities are from fundamental quantity, so we have this one as a basic unit of work. Then the last unit of work, which is number 3, is joule. Joule. Symbol is capital J. So these are the 3 units of work. As I said, the first one for the formula, that is Newton meter. The second one from FD, force, the kilogram meter per second square. Then this is another displacement. The unit of displacement is meter. So we now have kilogram meter square per second square, and which I said is the basic unit of work. And the last one is joule. Now, from this number 3 unit, which is joule, then what is joule? What is joule as applied to work? What is joule? Now, joule is the amount of work done or energy transfer by a force of 1 Newton by a force of 1 Newton in a distance of 1 meter. Joule is the amount of work done or energy transfer by a force of 1 Newton in a distance of 1 meter. That is why we said the first unit of work is Newton meter, and Joule is another unit of work, which is the SI unit of work. Work can be measured in larger units in Joule. That is, work can be measured in larger unit of Joule. That is, we have kilojoule, e.g. kilojoule, that is 1 kilojoule is equal to 1000 joule. Also, it can be measured in megajoule. Megajoule. That is mj. And 1 megajoule is equivalent to 10 raised to power 6 joule. So when work is want to measure in larger unit, then we can use kilojoule and megajoule. And 1 kilojoule is equal to 1000 joule. And for megajoule, 1 megajoule is equal to 10 raised to power 6 joule, or 1 million joule. Next is work done, and work is said to be done. Work is said to be done when a force moves body through a distance in the direction of the force. That is, work will be done when a force moves a body through a distance in the direction of the force. That is when work is said to be done. Now, in physics, as explained, there are some activities in which we can engage in and work can be done. And there are some activities in which we can engage in which will only lead to body exercise without work being done. So let's now look at the first one, activity. Activity in which work is done. Activities in which work is done. Don't forget, when work must be done, force must apply to the body and move a displacement, and the displacement must be in the direction of the force. So if force is applied and the displacement is not the direction of the force, then work is not done. That is what we call work done in physics. Force must apply, and the force must be applied to a body and move a displacement or distance in a specific direction. So, number one, a car climbing a slant E. Car climbing a slant E. Let's say this is a slant E. Then, and this is the car moving up like this. So when it cover a distance like this, the force apply. So the work has been done. Here, from here to here is the displacement. From here to here is the displacement, D. So when it cover from here to here with this force, then work has been done. 2. Number 2, a boy carrying a bus from the top of a table to certain height. That is, when a being carried from the top of a table to certain height, like as I said, this is a bus. This top of table carrying like this to a certain height, then work has been done. The force is upward, then the displacement from the top of table to this level. So that's the displacement in the direction of the force. So work has been done. 3. Is stressed catapult or rubber band. A stress catapult or rubber band. Let's say this is a rubber band. I want to apply work to be done. Then you stress it like this. The size, the length of this rubber band has been increased by applying that force. So work has been done. When you release it again, like this, and you stress it, so work has been done. Work is the product of force. Force has been applied and the displacement in the direction of the force. So the force applied and the displacement in the direction of the force. So on this rubber band now, force work has been done. Number 4, a weightlifter lift a weight from the floor to his head. A weightlifter lifts a weight from the floor to his head. Now, as I said, from example 3 and 4, a weightlifter lifts a weight from the floor to his head. And this is a weight. I want to lift this weight now. Work is being done that cover a displacement from the floor, and force is applied. And since it's being lifted from the floor to the head like this, work has been done. Work has been done from the floor to the head. So work has been done. That's another examples of activities in which work can be done. Next is examples of activities in which work is not done. That is, in physics, as I said earlier, if work is to be done, the work must be done, the force must be applied to an object, and that force that applied must take a displacement, and the displacement must be in the direction of the force. So if force is applied and no displacement of the object, then in physics, no work has been done. A typical example 1. Let's do the reverse of this one now. A weight lifter, put weight on his head. A weightlifter put weight on his head standing on a spot. Now this is weight, and the man carrying the weight is on a spot. As the weight is being lifted, although the weight is being lifted, but no specific displacement is covered. So the exercise done now is just to exercise body. No work has been done. This weight is being lifted like this for hours. The only thing we are going to see is the stress on the muscle. So no work has been done because this weight has not moved a distance. Therefore, we said there's no work being done in physics. A man pushing caterpillar. A caterpillar is an heavy machine. When somebody decided to push it, the person will not be able to push it on it or to cover any displacement or any distance in a specific direction. Therefore, such work, the work done on that one is equal to 0 since it does not cover any distance. 3. A woman carrying a 50 kg of rice on her head, standing on a spot. By the fact that somebody carry a 50 kg of rice, in normal sense, you would have think the person is doing a lot of work, but by putting a 50 kg of rice on her head, the load, that is the 50 kg of rice, have not carried to any displacement. So there's no work done. The work done is 0. Number 4, a boy puts a book on his head, moving along a level ground. A boy puts a book on his head, moving along a level ground. Now, this is a book put on head, moving along a smooth land, a smooth ground. Since this book has not moved a distance in a specific direction, then no work is being done. If it is on the head like this for hours, no work is done. That is, the work done is equal to 0. What are we saying in essence is that in physics, before work can be done, force must apply to the body together with displacement in the direction of the force. If the two quantities does not go together, then no work is being done. And the next thing is to look at magnitude of work done in various ways. The first one we are going to look at is work done in horizontal level. Work done in horizontal level. The work done once it is horizontal level, work done, the magnitude of work done will be equal to F, that is force, multiplied by displacement. That is work done in an horizontal level or horizontal plane. That's it, where W is equal to work done, as you said the other time, F is equal to force, and D is displacement. D is displacement. We use displacement if we want to use distance, since force is vector quantity and distance is scalar quantity. So if you use distance instead of displacement, you need to add in a specific direction so that you'll be able to tally with force. So by the time we use displacement, you don't need to add in a specific direction. So F is force, D is displacement. So we can now say the work done in horizontal level of your plane is equal to force multiplied by distance or displacement. And mind you, this displacement is not a vertical or perpendicular, it is an horizontal displacement. Horizontal displacement. That is work done in horizontal level or plane. Now the next one is work done against gravity. 2. Work done against gravity. Work done against gravity. For work done against gravity, when this weight is being lifted like this, force is applied, but the force applied is against gravity. So vertically like this, force applied is against gravity. So you now take the height from that floor to this height. That will be the height. So that is work done when you lift anything up against gravity. So work will be done against gravity. For that now, the work done, W will be equal to, since work is being done against gravity, and we say our work done is equal to force multiplied by displacement. Now, since it's being done against gravity, our force now be equal to mg, and this our d will be equal to multiply by the height. As I lifted all the weight the other time, if the height is taken, then we consider the height, then the mass of that weight. So where W is equal to work done, M is mass of object lifted against gravity. G, since it's being lifted against gravity, then acceleration due to gravity will have effect on it. G is acceleration due to gravity. And H, when you measure the H from that floor to the height that is being lifted, then A is the height of the object from the floor. Height of the object from the floor, or if it is coming down, it will be from that maximum height to the floor. And number 3, work done in an inclined plane. That is, when an object is an inclined plane, definitely work must be done also. Let's say this is an inclined plane, making angle theta to the horizontal, and an object is placed on this inclined plane, and force is applied like this. Then, since this one is an inclined plane now, don't forget, as I said the other time, if it is horizontal plane, since it's being horizontal, then it will be force multiplied by horizontal distance. Now, since force is multiplied by horizontal distance now, for this force now, for work to be done under this one, we need to resolve this one into 2 components. The first component is the horizontal component, which is Fs, and the second one is the vertical component, which is Fy. So if we now resolve this one now, since we know that work done is equal to F multiplied by distance, the displacement. But here now, since this one make an angle to the horizontal, this our F can be Fs and Fy. And if we want to look for this one, if it is, we now want to resolve horizontally. That is this F. So this F make angle theta. That is why we call it in an inclined plane. It will have 2 components, as I said. The horizontal component, which is Fs, and the vertical component, which is Fy. So if you want to resolve this F to horizontal component, Fs, and vertical component, which is Fy. So for horizontal component now, this Fs will be adjacent, while F itself will be opposite. Then we are going to have cos theta will be equal to Fs over F. Therefore, our Fs will be equal to F cos theta. If that is the case, and from the beginning we said work done is equal to F multiplied by displacement. Since we want to resolve horizontally, this our F now will be Fx. Don't forget from the formula, this is when it is in horizontal plane. But when it is inclined plane, you need to resolve it to horizontal component and vertical component. And this is for horizontal now. We have our Fs to be F cos theta. Then remove Fs now, which is F cos theta. Then our W now, which is work done, will be equal to F cos theta multiplied by D. So when it is in horizontal component, we have this formula. And mind you, it is this horizontal component that will be in the direction of the force. So in direction of force F. If it is the direction of force F, because it's a horizontal component, then work is done. Now, for vertical component now, let's resolve vertically. If we resolve vertically, and as I said the other time, when we resolve vertically, we close the horizontal, which is Fs. We consider the Fy and this F. Mind you, this is the displacement covered by this object. So if you now give us, this is opposite and this is hypotenuse, that will be sine theta equal to Fy over F. So our Fy now will be equal to F sine theta. If that is the case, apply this one. Since this one is vertical, so it will be our work done now will be equal to Fy multiplied by D. And what is our Fy on the board? So work done will be equal to F sine theta D. And mind you, if you look at the direction of this one now, as I said the other day, the direction of this one is in the same direction of this force. Then that is why we say, according to the definition of work done, that force multiplied by the displacement, and the displacement will be in direction of the force. But if you look at this one now, this force, this is the direction, this direction of the force. It means if that is the case, here now, in the direction of this one, the direction is perpendicular to the direction of the force. That is this displacement now. This one now is the perpendicular to the direction of the force. Therefore, we can now say no work is done. Or in another way, say work done is equal to F sine theta D equal to 0. That is, must be in the direction of the force. And this one is perpendicular, not in the direction of the force. So the work done on vertical axis of component is equal to 0. This is the convenient point to stop for now. In our next lesson, we are going to use this various formula on work done to solve some problem. And if you are just joining us for today, please try as much as possible to like, share, and subscribe. So when I upload a new video like this, you will be able to get the notification in time. Thank you.